Okay, any questions? So today we're going to finish up acids and bases. We'll review a chart with the bases and how you match them with functional groups to get the deprotonation to happen. And then we'll get into alkanes. So we'll talk about nomenclature, and then the big thing is we'll use the model for conformational analysis. That's how bonds rotate. And depending on the relationships, how they rotate, that's how we can predict outcomes of reactions. So we had left off on these different bases and the choice of solvent. So all reactions are run in liquid solvent. So solvent is also an organic molecule, so it has its own functional groups, and we need to ensure that the base does not react with the solvent. And so we drew this line right about here, and you can see from those bases on the top three, the conjugate acid is used as the solvent. So essentially, if we look at, say, sodium methoxide. So for example, if you take methanol, so as a liquid, and you add sodium metal, that is going to generate sodium methoxide in methanol. So that's your base, and then it's in that conjugate acid solvent. So the first three are what we call polar and protic, so they have OH. Then the last three, since they're strong bases, you can't use a solvent that has OH or NH because the base will just react with it. So in that case, you have to use an aprotic solvent. So if you have A before something, that just means without. So without an acidic proton. And so as we see, the functional groups are typically alkanes or ethers. So diethyl ether or tetrahydrofuran. And then dimethyl sulfoxide, or DMSO, is another one. So THF, it's a cyclic ether. DMSO, DMSO is a sulfoxide. The sulfoxide is a sulfur-oxygen double bond. So you'll notice when you transition from the alkanes to the ethers, so we know alkanes are nonpolar. Ethers have polarity due to the CO bonds. And then when you get up to like DMSO, that's really polar. So not so much in this module, but module 4, well, the solvent polarity will matter based on what type of reaction we're running. We classify things as either single electrons moving, those are called radical reactions, or when two electrons move, those are called ionic reactions. So you have to match the solvent polarity to the type of reaction you're running. So on our next slide here, there's a literal buffet of stuff on the table. So let's walk through it to understand what the sort of stoplight green, yellow, red means. In the first column, there's those bases. then you see the formula. And when I say pKa, that's the pKa of the functional group, or excuse me, the pKa of the conjugate acid of the base. And then the rest of the columns, maybe I'll just highlight those in red, or no, I'll highlight it in blue just so it's different. So what I'm highlighting in blue, those are all the common functional groups. And so you use this table to basically match what is the appropriate base to deprotonate an acidic hydrogen in that functional group. So for example, say we had a ketone. We want to deprotonate a ketone. So the things in yellow, the bases in yellow, so these top three, they'll deprotonate it, but most likely in a reversible fashion. Then the bases in green, those will do irreversible deprotonation. So you're favoring the products. And the take-home message is wherever there's green, that's the most appropriate base to use to deprotonate that functional group. So any of these 6 bases, when reacted with a carboxylic acid, will fully deprotonate them. If you had, say, an amine, an NH bond, you'd have to get down to the stronger bases to fully deprotonate them. So any questions on that? I think it's probably best seen with an example. So let's consider the molecule in the center of the reaction here. So this is a ketone. It's commonly called acetone. It's nail polish remover, basically. So acetone has one unique set of hydrogens. We have these carbons here, these alpha carbons, and I've shown one hydrogen. The pKa of that ketone alpha carbon H bond is 20. And if we want to go to the right, so this arrow means irreversibly. If we want to irreversibly deprotonate it, where we're only forming that carbon anion, what base would we use? To the left, we're still forming the same base, but now this is reversible. So pay attention to those arrows. So if we want to irreversibly deprotonate acetone, we have to use a very strong base. And so when we look at the second column in the responses, we can see that choices B and C, those are not strong bases. And then if we want to reversibly deprotonate, that's when we would use a relatively weak base. So the remaining responses A and D, A would be the most appropriate choice because choice D, both of those bases are strong. And so what's the logic of this? How do we sort of quantify things? So the conjugate acid of this base here, which is abbreviated LDA, is that amine. So that base abstracts that proton, you generate that amine. And we saw the pKa of that's about 40, 45 or something. And so then we have that difference. Which is actually a 10 to the 20 difference in acidity. If we do the same for potassium tert butoxide, the conjugate acid of that base is that alcohol. And so alcohols are about 16. So we get a delta pKa in terms of the absolute is about 4. And we remember we want to be above about 5 for it to be irreversible. So when you're below 5, you have this reversible situation. And again, that will come into play as we learn more reactions, and then definitely in Organic 2 when we really focus on acid-base chemistry more. Any questions? So really, when you look at a molecule, you define the uniqueness sets of hydrogen. The thing you're going to do next, go to the pKa table, look at what sort of functional group is to find the pKa values, and then you have to find a base that's strong enough to deprotonate that hydrogen. So we started off talking about the 3 different theories of acidity, so Arrhenius, Bronsted, Lowry, and then Lewis. And we said that the Lewis definition was the most general because it's talking about the movement of electrons. So now we're going to look at some Lewis acids. So again, a Lewis acid is an electron pair acceptor. And so do I have that anywhere? I think I do sort of here. So Lewis acid, so electron pair acceptor. And so I'm showing you 2 reagents on this slide, boron trifluoride and aluminum trichloride. In the periodic table, we have boron, carbon, nitrogen, oxygen, fluorine. And then I just remember the groups. So remember the group is something that just goes down. So this is group 3, 4, 5, 6, and 7. What you'll notice about boron and aluminum, so aluminum is under boron. They're only showing 3 bonds, right? So 3 times 2 is 6, and we're talking about, in general for this class, the octet rule. So that means the boron and aluminum are electron deficient. And so they have an unhybridized p orbital that's empty. So if we know that 2 electrons can go into an orbital. And so these are defined as Lewis acids because that orbital is empty. They can accept electrons. And so the little cartoon here, that's the p orbital. So which means you can react these things with reagents that have a lone pair of electrons. So now we can define things in the Lewis acid-base sense. So if we have BF3, So the boron is tri-coordinate. We have an empty p orbital, and we want to react it with an aldehyde called butanal. So a 4-carbon aldehyde. What would these things do to one another? So this is the Lewis acid, and then this is the Lewis base. We see that the oxygen of the carbonyl has 2 lone pairs. So we're going to start drawing an arrow from one lone pair into that empty p orbital. That means we're forming an oxygen-boron bond. And so that forms a complex. Notice now in this definition, we're not doing a proton transfer. So it forms that OB bond. But what's weird or different about that complex? We're still not done sort of completely drawing it. Because we know that oxygen normally has 2 bonds, 2 lone pairs. It doesn't look like that anymore. So we need to account for that somehow. So it's no longer in the neutral bonding pattern. We have to show charge. Yeah. So yeah, we'll add a plus to the oxygen. So that's just calculating formal charge. If the oxygen's plus, the boron has to be what? It has to be minus. So you're starting neutral and neutral. The bonding patterns are no longer neutral, so you have to draw these charges. But the charges still have to balance out to 0. You can't create an excess of plus or an excess of minus. So what's the point of this? Again, we can't learn everything at once, but in organic 2, you're going to learn reactions where this type of carbon of a carbonyl undergoes attack. So it gets attacked by something. The point of adding the Lewis acid is it helps whatever is attacking that carbon to do it a little bit easier. So the carbonyl group gets activated by that Lewis acid. So that's summarized here on the next slide, just to point out, as I'll highlight in green here, the arrow starts from the lone pair, and then it's pointing to the electron deficient atom. And then we have to make sure we account for the charge, the plus on oxygen, the minus on boron. So I think with that, that's the end of acids and bases for now. But again, keep in mind, we're sort of introducing it, and then we'll learn how to apply these things later. Any questions at this point? So I guess what I can say, moving forward from this point in the semester to the end, and then if you go on to Organic 2, the way that I organize the class is we're starting from sort of very simple compounds, alkanes. And then we learn reactions, and we're building up the oxidation state. So right now we're just dealing with CC and CH bonds. As we start learning more reactions, we're going to take something that's an alkane. We're going to introduce a functional group into it so it's more polar. And then from there, we'll learn these words substitution and elimination. And really, this all starts with the the constituents of petroleum, so crude oil. So that's what a lot of things are made of. So crude oil is, this substance that's pumped out of the ground. It's not one thing, it's many things. It has many constituents. And so what happens is it's pumped out of the ground, it's taken to these refineries, and then a way that it's purified is through distillation. So have you done distillation in lab? Not yet? So think of distillation as you're boiling your water to make pasta. So you see the liquid, then you see the steam come off. So what happens is the steam is collected. So it goes up this pipe, it's cooled, and then it's recollected. Now imagine instead of having just water, which is one thing, you have all these organic molecules. And we know already that with constitutional isomers, since they have different structures, they have different boiling points. So you can distill off the lower boiling things, and the pot residue is higher boiling. You add more heat, and then you purify these things through distillation. So like, for example, one cut of crude oil is gasoline. So gasoline is not necessarily pure. It can be a mixture of different hydrocarbons. So we've seen the three functional groups that are hydrocarbons as alkanes, alkenes, and alkynes. There is the general molecular formula. So we use this one, CnH2n plus 2, for degrees of unsaturation. And then we know that alkenes have a pi bond and alkynes have 2 pi bonds. So if you haven't seen this movie with Daniel Day-Lewis, has anyone seen this movie, There Will Be Blood? So one person has seen it. I would recommend you watch this. He's basically this prospector looking to strike it rich. He puts the work in, he finds a patch of ground that produces some oil. He buys more and builds this empire. It's based on a book by Upton Sinclair called Oil. And it really highlights how crude oil has transformed our lives. I mean, a lot of stuff that we use comes from these sort of bulk commodity chemicals, and then they're transformed into medicines, materials, agricultural products, all of that stuff. So what we want to understand now is how can we take an alkane and then turn it into something else? So that's the essence of organic chemistry, something we can use for our benefit. So we'll start with nomenclature. It's not the most exciting stuff in the world, but there are rules we can follow to name things, and it's kind of intuitive once you understand the general rules of it. So here I have the carbon counts 1 through 10, and these are names you should just commit to memory. And then the 3 columns, how the name changes based on the functional group. So notice I've underlined. So we have alkanes, alkenes, and alkynes. So there's only one carbon count alkane, that's methane. There's none for alkenes and alkynes because necessarily to have a pi bond you need 2 carbons. So for ethane, what it's telling you is because it ends in ane, it's an alkane. If we change the functional group to an alkene, the A becomes an E. So now the first 3 letters are the same, F, ETH, and then we swap out that A for an E. That's indicating to you there's a pi bond. And then alkynes, we have ethyne. one of the things, as you're reading your textbook, you'll have to look out for are common names. Ethine is typically called acetylene. And then you can see carbon count 3, propane, propene, propyne. So one of the skills you need to have, if you're given the name propyne, how do you draw it? So you need to convert the term into the structure. So prop is telling me there's 3 carbons. The yne is telling me there's a double bond. So 1, 2, 3, a triple bond. So triple bond, that's 2 carbons, and then that's the 3rd carbon. So that's fairly straightforward, but keep in mind of all the functional groups that you've learned, there's nomenclature for all of them. But the suffix, so I'm going to draw a line right here. In the rules, the suffix is telling you the parent functional group. And sort of the prefix is telling you the carbon count. So how many carbons are in the chain, and then what is the main functional group present? Really, where it becomes an issue is sort of here between 3 and 4. So that's what we'll spend some time on. Because remember, when we get to those higher carbon counts, you can then have constitutional isomers. And then that introduces sort of the rest of the nomenclature rules where on a carbon chain, where is something else located? What is the name of that something else? These are the rules as summarized. I'll read through them briefly, but the best way to do this is just by practicing things. The main thing is when you're given a structure, identify the longest carbon chain. So that gives you the carbon count. The way we'll do it, we'll circle it. That'll help us with sort of figuring out what's bonded to that longest chain. So after you circle it, you'll have things that are outside of that circle, and those are called substituents. So a substituent is anything bonded to the chain. And then once we have a substituent, then you sort of repeat the process. How many carbons does that have? You have to then alter the alkane name a little bit, and they're referred to as alkyl groups. So you do that, then you have to number the chain in a certain way so that the sum of all the numbers that's in the name is the lowest it can be. And then there's other sort of grammatical things like hyphens and commas, stuff like that we'll explain as we do some problems. Sometimes you'll run into identical substituents, and then we have to specify that in a certain way. We use additional numerical type prefixes. That's shown in this step 4. And then the logic of it is any substituent present, it's just listed in alphabetical order. There's a little nuance to this, but as you'll see as we walk through, it's sort of self-explanatory. So just a brief word on substituents. So these are things that are bonded to the longest chain. So what you're going to do is count the number of carbons in the substituent, and you modify the alkane name from ANE to YL. So a one carbon substituent is called methyl. 2 carbons ethyl, 3 propyl. So all the way down the table there. As part of doing this, one thing we want to all be clear on as we communicate is how things are classified, and we've talked a lot about this already. Classifying carbon and hydrogen. So in the first column, we can see the type. So a primary carbon is bonded to one other carbon. A primary hydrogen is bonded to a single carbon that's called a methyl group. So secondary carbon has 2 carbons bonded to it, tertiary 3, and quaternary 4. So that's sort of self-explanatory. The carbon of interest, you're just looking at how many other carbons are bonded to it. Then for hydrogens, we've used these terms methyl, methylene, and methine. And it's just the way when we learn reactions, I'll say, okay, the reaction is taking place at a methine hydrogen. And so there you know it's just a single CH. So we'll put this into practice by looking at some molecular formulas. As we've already seen, when you get to C4, that's when you can have linear or branched isomers. In the branched is the ones that will really put these rules into use. So C4H10. For any molecular formula, that's an alkane. There's really only one linear isomer. So for C4H10, that would be butane. But we also have a branched isomer. Now for it to be branched, we're starting with 4 carbons. It has to be 1 less carbon in the longest chain. So we know 3 carbons is propane. Now to get back up to the molecular formula, we still have a carbon left. So that carbon can only go in one place. It can't go on carbons 1 or 3 because then you just make butane again. So it has to go on carbon 2. And so if we apply the nomenclature rules, so we're going to circle the longest chain, that's 3 carbons. So I circle that in blue. So the parent is propane. And then at carbon 2, you have this thing sprouting off. You count it, it's 1 carbon. So 1 carbon is methane, but because it's a substituent, it's now called methyl. So to put all of that information together, what we end up with on carbon 2 is a methyl group. So we say 2 and then a hyphen. So numbers are separated from letters by a hyphen. So 2, methyl, and then the parent. So that's all one word. 2-methylpropane. So let's do C5. So C5H12. So we know the parent for 5 carbons is pentane. So there's only one of those. We're going to chop a carbon off, and the longest chain now is going to be 4. So now it's a butane derivative. So where should that 1 carbon atom go? You said 2 or 3? So we'll sort of draw this, like I'll draw the steps and I'll show you, because you said 2 things. One of them is right, the other is not, and I want to explain why. So there's the longest chain. We know it's now going to be a butane derivative. So we have to put that methyl group somewhere internal, either 2 or 3, but only one of those is right. I mean, ultimately they're the same compound, but in terms of how you name it, the name is 2-methylbutane. So 2-methylbutane. So that one's correct. 3-methylbutane is not correct, because the rules state the substituents have to get the lowest possible number they can on the longest chain. And we'll go through some examples where there's more substituents, and that becomes a little bit more apparent why that is. So 2-methylbutane. And then we can go down one more. So we started with 5, we went to 4. Now we can have 3 as the longest chain. So that's a propane derivative. And now we have 2 carbons to put back in. So where do they go? They both go on carbon 2. And so how do we now identify that? Because carbon 2 has 2 substituents. We say 2, 2. 2, 2. They're the same, so we say di. Then the substituent name methyl. And then the parent propane. 2,2-dimethylpropane. So the self-consistency in that is carbon 2 has two methyl groups. You specify their locations, and because of there's 2 numbers here, that's where you have to use this prefix di. If you said 2,2-methylpropane, that's technically not correct. So we got a little bit of space for C6H14. And we know that the linear one is hexane. So without me drawing anything, I'll just throw it out there. Communicate to me a name, and then I'll draw it up there, of a branched isomer that is a pentane derivative. Two-methyl what? 2-methyl pentane. So we're going to go from 6 to 5. So 2-methylpentane. So 3-methylpentane. So are there any more pentane derivatives we can draw? So no, because we can't have 4-methylpentane is really just 2-methylpentane. So when you look at the longest chain, there's 2 ways you can number it, from the left to the right or the right to the left. So now let's get into the branched ones that are 4 carbons long. Say it again. Yeah, so 2,2-dimethylbutane. So there's 4 carbons. We can put 2 of them on carbon 2. So 2,2-dimethylbutane. So 2,3-dimethylbutane. I don't believe we can go down to propanes, because by the time you get to the longest chain of 3 carbons, then you have 3 more to put in there. And really, you're just going to draw something you've already considered. So again, the take-home message is, find the longest chain, determine what the substituents are, and then follow like the grammatic rules with commas and hyphens. So here is just a table summarizing that. So the numbers in blue are the location numbers or locant numbers. And then we have the uniqueness set in what I've done. So for butane, there's 2 unique type of carbon, 2 sets of hydrogen. And then for the ratios, I put like T and Q. That's just telling you what sort of the multiplicity of those signals should look like. And again, that's just to always keep in your mind, how are you considering differentiating these isomers? As we learn reactions, a common question is, how do I predict the right product? Well, you really have to consider what are all the things that can form. And then of those possibilities, what is the data telling you? So let me just highlight something here real quick. And I'll draw these in red. So if we're talking about classifications, so that would be like a primary carbon. That would be primary. Those would be secondary. For the 2-methylpropane, we have primary, and primary, and then carbon 2 is tertiary. So the 2,2-dimethylpropane, this one is, that carbon's now quaternary. So it's bonded to 4 other carbons. And again, that exercise will guide you in Module 4 about determining where a reaction happens. Any questions so far? So here's a table. It's called enumeration of alkenes. It gets pretty complicated once you get up into past 7 and above. But as we saw, there's only one linear constitutional isomer, and then you see the rest of the columns. You're taking off one carbon at a time, and you'll see on the next slide some numbers filled in there. And this is telling you how many constitutional isomers there can be for each. So we did up to C6. If you want to practice, you can practice the nomenclature doing C7. When you get up to 8 and 9, you see like it gets there's a lot, right? So C7 has 9 total isomers. 8 has 18, 9 has 35, and 10 has 75. So the question marks I didn't bother to do. The problem with this is as you fill in these columns, it's making sure that you haven't proposed something you've already drawn, and it gets thick pretty quick. But it's a good exercise to help you understand the nomenclature rules. Any questions? So I know it looks like there's a crack in the screen of my iPad, but that's actually an organic molecule. So can you figure out the name of it? Did you say D? I don't think so. So really what you're doing is, when you look at these lines and bends and stuff, they're paths. And the first rule of the nomenclature, you have to walk the longest path. So I crossed off hexane. Hexane is 6 carbons. Of the other choices, you have nonane, which is 9, and octane, which is 8. I don't think so. What'd you say, B? I don't want to click forward yet. I want to figure it out. So again, the challenge is, one, you have to find the longest chain. And then once you do that, remember, you can number that chain 2 ways. So the way you number it is also important, because as I said, these substituent location numbers, they're individual numbers, but if you consider them and sum them, that has to be the lowest possible number it can be. So So what do we have? Let me I want to start here. I'm going to highlight. So that's 1 carbon. 2, 3, 4, 5, 6, 7, 8, 9. And I think we can go another path that gets us 9 as well. So
the other path is it's sort of the same name. Oh, the other path is
So the other path, so that gets us 2 paths, 2 different paths that are 9. But again, you can number each of those, forward or backwards. And so I want to say A is the correct answer, but let me peek the answer. So let's just look at that slide. So yes, A is the correct. So the paths in red are shorter chain lengths, so they can't be considered. Then the 2 paths, green and yellow, are both 9 carbons, so they're in the running. And so let's look at, change this to green here. So the numbering in green on that green path, that's the correct numbering. If I numbered it in red, that would be the incorrect way of numbering that. So let's talk about that, and then we'll talk about why the yellow one is not correct either. So you're given a structure actually to figure out the name, but when you read the name, really you want to start at the end to determine what the parent is, and then you're sort of then looking at the substituents. So it says 6-ethyl. Off carbon 6, there's a 2-carbon unit. Ethane becomes ethyl. Carbons 3 and 5, 3,5-dimethyl. And then carbon 4 has a 3-carbon chain propyl. If we numbered it the other way, what would that be? So 4-ethyl, 5,7-dimethyl, 6-propyl, nonane. So 2 things I want to point out. of these two choices, 4 is less than 6, right? That does not matter. The way you order substituents, E ethyl, M methyl, P propyl. Substituents always are listed in alphabetical order, regardless of the number attached to them. So the real reason that this one in green is correct versus the one that I wrote in red. So if we take 6 plus 3 plus 5 plus 4, that gets us what? $18. So that gets us 22. So the way in which you number that chain matters because the substituents have to get the lowest possible sum of their locations. The one in yellow, that's not correct. Basically, see this right here? So how are we numbering this? That's the problem there. Because of that substituent coming off, it says 2-butyl. And so what does that mean? You have a separate set of numbering on that chain, 1, 2, 3, 4. The 2 in there refers to that 2. If you include that pathway in the longest chain, you then make more substituents, which you get to choice A. So you can't really condense things, which is why C and D are wrong, because you're condensing a lot of carbon atoms into longer chains and naming them as substituents, like this hexyl here. So really, by finding the longest chain, you're ensuring that you have the maximum amount of substituents. And that reduces the overall carbon count in those substituents. So I think we have a couple more of these, and then we'll get to this issue right here. Notice in choice A, every substituent that's coming off is linear. But now in choice B, there's a branching. And that's why we have that 2-butyl rather than just butyl. So branching presents a problem. It's sort of shown there, but a lot of branch substituents do not use sort of their common names. Their formal names. They have these common names that are used. Check. I don't think. So are these the same things? Which of the following molecules is 4-ethyl 2,3-dimethyl octane? So again, breaking down the name, you're looking for 8 carbons in the longest chain. So there's the parent octane. Notice the substituents E comes before M, and then the numbers are just where they're located on the chain. B as in boy. So maybe I'll do some coloring here. So 4-ethyl, that's right there. 2,3-dimethyl, 2,3-dimethyl. And then octane, that's the longest chain. If you numbered that the other way, so up here you're getting 4 plus 2 plus 3, that equal 9. Down here you're getting 5 plus 6 plus 7, that equals what, 18? So again, you have to figure out the way to number the chains so the sum of the substituents is the lowest it can be. So I believe these are the same compound. Okay, so which one is 5-ethyl 3,4-dimethyl nonane? What? D. So and then we'll just do some coloring. So that's the way you would number it. So we'll call the ethyl the red substituent. The 3,4-dimethyl is the blue. Any questions? So I want to talk a little bit about when you have a branching substituent that's coming off that longest chain, which means that you're coming off the longest chain, and from there, instead of walking a single path, it can now branch off. How is that handled? So there are these prefixes used. So there's a prefix and then the carbon count. If you have 3 carbons, that's propane, and the attachment to the longest chain is, that ball is the longest chain. So of the substituent, if it's bonding to the carbon 2, we use the term iso, so that would be called isopropyl. Iso means same. The iso is then further abbreviated to I. If you have a 4-carbon, you can have isobutyl. A 4-carbon that's bonded to position 2. That's called secondary or S-butyl. 4-carbon that looks like a chicken foot, that's called tert or tertiary butyl. And then 5 carbons, that's a little bit bigger than the chicken foot before, that's called neopentyl. So what you're looking for is the discrete collection as its own substituent. The important thing to remember in terms of the alphabetical naming, the iso, secondary, tert, and neo are not considered part of the name. So you would use the P for propyl, the B for butyl, or the P for pentyl. So I think we have some questions here. It says name the following alkanes using the common names for branched substituents. We'll do the one on the left. So I can just tell by looking where I want to start numbering this chain. I want to start it on the right here is 1, 2, 3, 4, 5, 6, 7, 8. So that tells me it's an octane. Then at position 4, it's a 3-carbon substituent, so it's isopropyl. So that would be 4 isopropyl octane. So what about the one in the box? What do you think the name of that is? You said C. So remember the substituents have to be ordered first according to alphabetical, not numeric. So B, you have butyl and then ethyl. So the 7 tells us it's a heptane. And then off that we have an ethyl and a tert butyl. So we have 4 tert butyl, 3 ethyl heptane. So again, don't get fooled by 3 being a lower number in that it should be first. It's always alphabetical according to the substituents. And then the number is just coming along for the ride.
Would the names be the same if your longest path started at the carbon that's all the way to the left? Because the ethyl still comes off of the 3 even better.
Like that.
Yeah.
Yeah, you'd still get the same name because like this connection point, it's ethyl and ethyl. So in that case, it doesn't matter. So there are those 3 names for those. Again, that deals with branching substituents. So it looks like today we only have a couple minutes left to only really wrap up nomenclature, so we won't get to the conformational analysis until next week. So what about when you take a long carbon chain, you take the terminal carbons and bond them together, you get rings. And these are called cycloalkanes. So cycloalkanes, by definition, have 1 degree of unsaturation. That's the ring. So you minimally have to start at 3 carbons, so that gets you cyclopropane. going up cyclobutane, cyclopentane, etc. You can see for these carbon counts, CnH2n, and again, these all have a ring. For C4H8, what I mean by the N ring, that's cyclobutane. We can draw a constitutional isomer that takes it down one ring size. So now that's a cyclopropane derivative, and we have one carbon left, so that would be called methyl cyclopropane. And it's the same logic as we did before. So that gives you an opportunity to practice nomenclature. As you can see, there's a lot of yellow in here. I haven't spent the time figuring out what these all could be because, once you get up to C6H12, you can see there's quite a bit of isomers you can draw for that. So C7H14's got to be a lot. But that's a way to practice them. So practice drawing, practice the nomenclature, figuring out uniqueness, and then thinking about NMR. We'll end on this slide today. It's kind of a niche topic, but we're going to see it in certain circumstances moving forward. So I call these higher order cycloalkanes. And really it's when you have two ring systems. There are two types, bicyclic and spirocyclic. What I want to give you a couple seconds here, 30 seconds or so, look at the nomenclature for bicyclic compounds and see if you can make sense of what it's telling you. So for example, bicyclo square bracket 1.1.0 square bracket butane. How many total carbons are in this molecule? Huh? 4? So we have 4 total carbons. So that gets you the butane. They all have bicyclo in front of them. So what does the 110 mean? Do you see the connection?
They're all divisible by 2. It's a connection.
I guess I.
The bicyclo 2,1 contain has these ones.
What?
It's like a ratio, like 2 are shared and 2 aren't.
Kind of. That's one way of thinking about it. So you have 2 rings. The ones I'm drawing in red, they're shared by a bridge, right? How many carbons are on that bridge? So the start and the end. But if you walk from one to the next, you don't encounter any more, right? So that's the 0. So this is 1 carbon, 1 carbon, and then 0 on the bridge. So if you look at this one, bicyclo 2, 1, 1. So there's 1 carbon, there's 1 carbon, and then you have 1 and 2. So really what it's telling you is, as you walk from the bridge heads, how many carbons are you encountering on each path? So on this one real quick, highlight in red, here's the bridgehead. If you walk from those 2 red dots, you encounter none, so that's 0. If you walk this path, there's 1. If you walk this path, there's 2. the spirocyclic ones, you have the total number of carbons preceded by spiro, then these numbers 2 and 2. They're always joined by a quaternary carbon. So that's assumed in the word spiro. The 2 and 2 are the numbers of carbons you cross to get back to where you started from. So if you start here, you walk 1, 2, and then you're back where you started. So we start here, 1, 2, 3, and you're back where you started. So 2 and 3. So we ran a little bit over, but we'll encounter some of those compounds as we move forward in this module. And then on Monday, we're going to start with using these models to do rotations and dihedral angles. So